Welcome to Lecture 36, in which I get to introduce a new phenomenon which I think is one of the most fascinating in electromagnetism and indeed in all of physics. And it's so fascinating and so practical and so important that I'm going to devote 2 full lectures to it. This one more about the theory, the next one more about applications. The phenomenon I'm talking about is electromagnetic induction. And for the first time, it gives us a direct relationship between the electric and magnetic fields. So that convergence of electricity and magnetism into a single unified field is going to continue importantly throughout this lecture and then in more practical applications throughout the next one. So let me begin with some important experiments. I'm going to make these experiments very simple intentionally so you can see exactly what's going on. So over here I have a coil of wire, a nice simple homemade coil of wire, nothing fancy or hidden about it. It's just a bunch of turns of wire with tape wrapped around to hold it together. And it's connected to a very simple meter that reads electric current. So there's no electronics in this, there's no battery, there's nothing to plug in. It's just a needle that reads when electric current flows. And I'm going to do several experiments with this system. So let me begin by taking one of my big bar magnets. Now, there's no source of electrical energy here at all. No battery, nothing's plugged in, nothing. Here I have just a magnet and my muscles. And I'm going to thrust this magnet at that coil, in fact, through that coil. There I go. And you can see that needle move as I do that. Again. In fact, if we look more carefully, as I thrust it in, the needle moves one way. As I pull it out, it moves the other way. In to the right, out to the left. In to the right, out to the left. Keep doing that, and I've got a current that's flowing in 2 different directions as I move the magnet back and forth. Something about the motion of this magnet is causing an electric current in this coil. Let's do another experiment. This time I'm going to hold the magnet steady, and I'm going to move the coil. Same effect. Now, you might think that's kind of obvious. Well, when I move the magnet, I got that effect, so why not when I move the coil? Well, that's good thinking. Actually, that thinking is so profound that thinking about the reciprocal nature of these 2 experiments figured in Einstein, the first paragraph of Einstein's theory of relativity. The first paragraph of the statement in which he introduced the theory of relativity discussed exactly the relationship between this experiment and this experiment, because the description of those 2 experiments in electromagnetic theory is quite different, but the outcome is exactly the same. Remarkable. So there's a second experiment. Let's do a third experiment. This was a bar magnet. Now, we learned in the previous lecture that magnets are essentially originating in moving electric charge. In the case of this bar magnet, tiny little atomic current loops and electron spins. But we also know that we can put currents through wires, and that also gives rise to magnetic fields. So I have here another coil, basically identical to the first, except I've used red tape on it so we can distinguish them. And I've got it connected to my power supply, and I'm going to put a hefty current through it of about 7 or 8 amperes. It's getting warm, so I'm not going to do this for too long. And I'm going to move my black coil near the red coil. So here we go. And you can see, again, the needle is moving. And if I do the reciprocal experiment, move the red coil near the black one, you can see the needle moving again. Now, that shouldn't surprise you. It shouldn't surprise you because, after all, this red coil, although it looks very different from this bar magnet, has in fact become a magnet. And they're both basically dipole-like fields surrounding this coil and the bar magnet. Even though they look very different, they're very similar entities once they have a current passing through this coil. The current's still there, by the way. Now I'm going to do one other thing. By the way, you'll see some interactions among those, which is not surprising because they're both magnets. I'm going to turn off the current. And you see the needle jump when I turn the current off. I'm going to turn the current on, and you see the needle jump. Now, right now, there's a steady current of almost 7 amps flowing. That's a lot of current, making this coil reasonably warm. But there's nothing happening on the meter. When I turn the current off, something happens. When I turn the current on, something happens. In fact, if I grab the voltage control knob here, which will also control the current through Ohm's law, and I start wiggling it back and forth, you see the needle moves as the voltage changes and consequently the current changes. So there are 4 distinct experiments. What do they have in common? They're all experiments about this phenomenon I want to talk about today of electromagnetic induction. So let's look at what these induction experiments have in common. First of all, first experiment was move a magnet near a coil. I got what I'm going to call an induced current, induced by the motion of the magnet. So there's a little diagram of pretty much what I had, a coil with only one turn. I had multiple turns, but same thing. I move the coil near the magnet, the reciprocal experiment, I get the same result. I pass current through one coil, and I move the second coil relative to the first, or vice versa, and I get current induced in that second coil. Again, not surprising, because the first coil with current through it acts like a magnet. And interestingly, I change the current in the first coil, and I get this induced current in the second coil. So I want to ask the question, what do all these experiments have in common? They have in common changing magnetism. Magnetism was changing in all those cases. In the first case, as I moved the magnet toward the coil, the magnetic field in the vicinity of this coil was getting bigger. In the second case, I moved the coil near the magnet, same thing was happening. In the third case, I passed current through the coil and it became a magnet, so it was like the first 2 experiments. And in the last experiment, in which I turned the power supply on or off, or I wiggled the voltage knob, I was changing the current and therefore changing the magnetic field. So all these experiments, all these induction experiments have in common changing magnetism. So that's a great big takeaway idea. 10 years from now, when you've forgotten about this course, I do want you to remember that changing magnetism causes these induced effects, and we'll explore these induced effects more both in this lecture and the next one. So let's look in a little more detail at this phenomenon of electromagnetic induction. Clearly electromagnetic, because we're involving both electricity and magnetism. So our experiments show that a changing magnetic field induces a current in a nearby complete circuit. More fundamental is this fact. A changing magnetic field creates an EMF, that funny word I used for a source of energy in an electric circuit, approximately the same thing as voltage, but not quite, in a conductor. So if I have a conductor and a changing magnetic field arises near that conductor, I get a voltage. Basically. It drives a current if there's a complete circuit. Still more fundamental, as we'll see at the end of this lecture, a changing magnetic field creates an electric field. So we have a new source of electric field, something in addition to electric charge. There are 2 ways of making electric fields. You can have electric charges that produce electric fields in the space around them, or you can have changing magnetic fields, and they also produce electric fields. A new kind of electric field, one that, by the way, is not a conservative field, unlike the one produced by electric charges. So let's quantify this. Let's look at it in a little more detail. Changing magnetism makes electricity. Big takeaway message again. But let's get quantitative. So let's look at this statement that changing magnetism makes electricity. That statement is embodied in one of the 4 fundamental laws of electromagnetism. It's called Faraday's law. And it says voltage induced in a circuit is the rate of change of what's called magnetic flux through the circuit. And for the symbol for magnetic flux is a capital Greek phi with a sub b, b for magnetic field, to remind us it's associated with magnetic field. And the statement of Faraday's law in this context says the magnitude, and I put absolute values around it to show I'm just talking about the magnitude. I'll talk later about the sign. The magnitude of that induced voltage is simply the rate of change, delta phi b over delta t, the rate of change. By the way, those of you involved who know calculus, those deltas should really be d's, and we're talking about derivatives. But rate of change, I'm using delta to mean rate of change. So the magnetic flux is the product of the field with the circuit area. That's how magnetic flux is defined. It's kind of a surrogate for the number of field lines emerging or passing through a surface. In this case, an open surface, a surface bounded by the circuit we're talking about. You can calculate it easily just multiplying area by magnetic field if the field is uniform. If it's non-uniform, you got to use some calculus. And it is a surrogate for the number of magnetic field lines that pass through the circuit area. So here is an example of magnetic flux. I've got a uniform magnetic field. I've got a circular loop of conductor at right angles to that magnetic field in this perspective drawing, and the magnetic flux through that loop area would simply be phi b is b times a. So here's our takeaway statement. The induced voltage is the rate of change of magnetic flux. How do we change magnetic flux? Well, there are several ways to do it. I could change the field, because that goes into the expression for magnetic flux B times A. So here's an example where I'm moving the magnet toward the coil, and the field lines are getting more intense toward the magnet, so the field is increasing. I can change the field. I can change the area. So if I start with a big area, and I somehow shrink it to a smaller area, I've changed the area, and I've therefore changed the magnetic flux. And in both cases, I've induced a voltage in that loop. Or I could change the orientation of the area relative to the field, and that would also change the amount of field going through that area, so that would change the magnetic flux. So 3 ways to change magnetic flux. Let's do some experiments and take a look at those. So here's a magnet, just a stationary magnet. Here's my coil. One way to change the flux is to move the magnet near the coil or the coil near the magnet. We've done that before. But another way would be to change the area without changing the magnetic field. Change the area by distorting the loop, and you can see the needle move just a little tiny bit. Or I could change the orientation. I could spin that loop around. In fact, that's what's going on in all the electric generators that are generating all the electricity that you use. There are spinning coils of wire in magnetic fields, much bigger coils of wire in much stronger magnetic fields. We'll see more of that in the next lecture, but that's how electric generators work. So 3 ways to change the flux through a circuit. You can change the magnetic field, you can change the area, or you can change the orientation. We tend not to use the area one as much as we do the other 2. Well, that's an introduction to this Faraday's law of electromagnetic induction, but that's only the magnitude of this induced voltage. What about the direction? Well, before we do the direction, let's just look at one simple case where we would want to use the magnitude quantitatively. So let's go over to our big screen where we do our math and look at a special case, simple case. So here is a very simple example. I've got a single loop of conducting wire. I've got a light bulb connected in that loop of conducting wire. Let's say the light requires 3 volts to light at full brightness. It's in a wire loop 20 centimeters in diameter. How rapidly do I need to change the magnetic field for that light to full brightness? Well, magnetic flux is the magnetic field. It's uniform into the screen here, times the area. That's B times pi r squared, the area of a circle. That is the rate of change of flux. Well, the area isn't changing, so pi r squared stays the same. So that's pi r squared times the rate of change of the magnetic field, and that's what we're going to be looking for. So the rate of change of the magnetic flux, which is the voltage, is pi r squared delta B delta T, the rate of change of magnetic field. Faraday's law says the induced voltage is equal to that rate of change of magnetic flux. So we would like that rate of change to be 3 volts. So let's solve for dB dt. Or delta B delta T. Delta B delta T is 1 over pi r squared times the rate of change of flux. And we want the rate of change of flux, which Faraday's law says is the voltage, to be equal to 3 volts. So there we are. Its radius is 0.1 meters, 1/10 of a meter, 10 centimeters. The diameter is 20 centimeters. Work out the numbers. And we've got to change that field at 95 teslas per second. Now, a Tesla is a big, strong magnetic field, so that would be really impossible. After 1 second, we'd have an enormous, enormous magnetic field. But what we could do in practice is wind many, many hundreds, thousands of turns of wire, and each one would have the same voltage induced in it, and they'd all be in series, and so we could easily do this with a much smaller change in magnetic flux. But there's an example of using Faraday's law to calculate the value of an induced voltage. Okay, so now let's look at questions of the direction of this induced magnetic field. The direction is so important that it's given its own name, even though it's part of Faraday's law. And the direction is the law that tells us the direction is called Lenz's law, and it says the direction of any induced voltage or current is such as to oppose the change, giving rise to the induced effect. Let me give you a sense of what I mean by that. Here's a coil of wire. Here's a magnet. I thrust the magnet at the coil of wire, and current flows in the coil of wire, and since the wire has resistance, that current results in the wire getting warmer. So, in principle, that's got to be hard for me to do that. I've got to do work to push that magnet through that coil. What causes it to be hard for me to do that? And in the next lecture, we'll see some examples where it gets really hard. Right now, I don't really feel much. What would cause that to get hard? Well, here's the north pole of my magnet, the red pole, coming toward that loop. How could it be difficult? It could be difficult if this bar magnet were facing another north pole and feeling a repulsive force. That would make it hard to move. How could I get a north pole out of this loop? How can I make this into a magnet with a north pole? I could do it by having a current flowing in this direction. And if you look at the diagram, you'll see, as I do this, you'll see that the current ends up flowing in this direction, and that gives rise to a magnetic field that, in this loop, points that way. Or you can also think about it as the direction of my thumb, a right-hand rule. Current goes that way, makes a magnetic field in the interior of the loop that way, and that makes the loop's magnetic field have its north pole there. And so, when I grab the magnet and thrust, I'm really trying to bring two north poles together, and it's hard to do. And so I do work. That's Lenz's law. If Lenz's law weren't true, energy conservation wouldn't hold. If Lenz's law weren't true, all the electric generators at all the power plants would turn on their own without anybody having to do any work, burn any fuel, fission any uranium or anything. The whole energy problem would be solved. It's essential for energy conservation, for electromagnetism to be consistent with energy conservation. And mathematically, Lenz's law is expressed by a minus sign in Faraday's law. And here is Faraday's law written all out now carefully without those absolute value signs to give me the magnitude of the induced voltage, the value of the induced voltage, with its sign, with its direction, with the directions of the associated currents, is given by that minus sign and then the rate of change of magnetic flux. In practice, we don't try to calculate direction from that minus sign. We sort of calculate the magnitude of the induced voltage like we did for that light example, and then we figure out what the direction should be from the fact that the direction of the induced current has to be opposite the induced effect, to try to stop the induced effect from occurring. So that's Lenz's law, and let's look at just one example of Lenz's law. Here it is. I've got a little demonstration here in which I have a coil of wire, many, many turns of wire, on a post. The post has a ferromagnetic material in it to strengthen magnetic fields. I'm going to pass a rather large electric current through that coil for a brief time when I push down on that switch. And here I have a little aluminum ring. Just a piece of aluminum. Aluminum is a fairly good conductor, not as good as copper, but pretty good. I'm going to put that, but it's a lot lighter, sometimes cheaper. I'm going to put that aluminum ring over here, and the aluminum ring is actually going to be more dramatic for this experiment. And when I push down on this switch, I'm going to induce a big current in this coil, and it's an alternating current, so it's changing very rapidly. And it's going to make a changing magnetic field. That changing magnetic field is going to induce a current in this aluminum ring, and that current is going to be in such a direction that the ring makes a magnetic field that opposes the magnetic field of this loop. This current's going to flow in the opposite direction, in fact, and we found out last time that opposite currents repel each other, and here's what's going to happen. There we go. Those forces ended up in a rapid acceleration of the ring and a repelling of the two coils of wire. So that's an example of Lenz's law, showing that effect, that induced effects, induced currents, are in such a direction as to oppose the effects that give rise to them. And I want to spend most of the rest of this lecture on a very important calculation, more detailed than some of the calculations I've been doing in this course, but I want you to understand just how profound is this relationship between electromagnetic induction and the conservation of energy. Conservation of energy being a really crucial idea in physics, and somehow here this new electromagnetic phenomenon knows about it and is consistent with it. And I'm going to do a rather lengthy but sophisticated, and somewhat sophisticated but also somewhat simple calculation that convinces you that electromagnetic induction is consistent with conservation of energy as we learned it when we studied mechanics. So I'm going to have a simple system consisting of a couple of electrically conducting rails. Picture a railroad track, for example. They are spaced a distance C apart, and they're spiked down to the ground or glued in place. They're not going to be able to move. Across the end of them is connected a resistance R. Otherwise, they're electrically insulated from each other, except at this resistance R. The whole thing is sitting in a magnetic field, which is pointing, in this case, into the screen. That's what the X's mean. And there is a bar which is free to move. It slides along the rails. It's all greased nicely, so it's frictionless, but the bar is also a conductor, and it is in electrical contact with the rails. So I have a complete loop here, an electrically conducting loop, just like the circular loop I was holding, except it's rectangular, and I'm assuming there's no resistance anywhere except in that resistor. And what I'm going to do is pull this loop to the right, or pull this bar to the right with a constant speed V. Okay, now we're going to have two V's in this problem, because we're going to have V for velocity, that's the lowercase one, and V for voltage, that's going to be the uppercase one. Don't get them confused. So I'm going to pull the bar to the right with a constant speed V. And I want to know the rate at which I have to do work to pull on that bar. Now, if the bar were just sitting there and we didn't have electromagnetic induction going on, it would take no work to pull a bar at constant speed, because it takes no net force to move something at constant speed. So once I got the bar going, it would just go by itself. But I've got electromagnetic induction going on. So I want to know the rate at which I have to do work to pull on that bar. And I want to know the rate at which electrical energy is dissipated in that resistor. Now, those sound like two entirely different questions from two entirely different branches of physics, electromagnetism and mechanics. Mechanics, what rate do I do work? Electricity and magnetism, at what rate is energy dissipated in that resistor? And I'm going to convince you that those two are exactly the same, that somehow this system takes the mechanical work that I do to pull on that bar and it converts it into, ultimately, heat in that resistor. So let's go and see how that works. So here's kind of a picture of the setup without the motion, but showing the motion by the V arrow and the indicator that we have a velocity. And I've also shown the bar when it's a distance x from the beginning. So it's moved that distance already. V is into the screen. There's the resistance, and we're ready to go. What's the loop area? Well, we have a loop here. And the loop area, at least the part of it that's in the magnetic field, that's all that counts, is the spacing d, the rail spacing d, times this distance x. It's a rectangular area, and the area is a times dx. That's d times x. If you're a calculus type, it's not dx the infinitesimal, it's d times x. We know how to calculate magnetic flux, this symbol capital Greek phi. It's the magnetic field, in this case uniform, so we can just multiply, times the area. So that's b times dx, because d times x is the loop area. Why do we want the magnetic flux? Because induction is about changing magnetic flux. So we don't actually want the magnetic flux. We want the rate of change of magnetic flux, but we'll get there. As the bar moves, you can see that the area is going to increase. The area bounded by the conducting circuit, the bar, the rails, the resistor. As the bar moves, that area increases. And consequently, the flux increases. One way to increase flux is to increase the area. That's why that's happening. So let's calculate the rate of change of the magnetic flux, because that's what goes in Faraday's law to give us the voltage that gets induced. So there's the rate of change of flux that I'm trying to calculate. The magnetic field in this case is not changing. One way to change magnetic flux is to change field, but that's not what we're doing here. We're changing the area. So B is a constant. It just stays there, and we have to multiply. We have to find the rate of change of the area to find the rate of change of the flux. Well, the area was the product of the spacing and the position x, and the spacing isn't changing either. The rails are just sitting there glued in place. What is changing is x. So that's what's giving us a change in flux, the change in x, which is making that area change, x being this distance. Well, so we have b times d, those are fixed, times the rate of change of x. But what's the rate of change of x? Think about that a moment. What is it? It's just the velocity v. So this expression, b d delta x delta t, becomes v. What does v mean? It means the rate of change of position, way back from the early lectures on kinematics. That's what velocity is. So there is the rate of change of magnetic flux. There it is. So we've gone through a lot of calculations, gotten that result. Faraday's law says the magnitude of the voltage is the rate of change of magnetic flux, so the magnitude of the voltage is b dv. Ohm's law tells us the current. The current is V over R, B dV over R. We're getting there. What's the direction of that current? It's counterclockwise. And you can see that in two ways. One simple way to see it is to ask yourself, what's the direction of the magnetic force on charge carriers in this wire when you drag them that way? And if you do the right-hand rule, you'll find it's up. So charge is going to move up toward the top of the bar and send a current around that way. But the more sophisticated way to look at that is to use Lenz's law and say, okay, the direction of that current has to be such as to oppose the change that's causing it. Now, what's the change that's causing it? The change that's causing it is this increase in magnetic flux. How can a current try to slow that increase down? How can it do that? Well, what currents can do is make magnetic fields. So what the current could do to reduce the magnetic flux when it's increasing, but try to reduce it, is to make a magnetic field that opposes the magnetic field that's associated with that induced effect. That's the magnetic field into the screen. So the induced current would like to make a magnetic field. I'm talking awfully anthropomorphically about what's going on. It doesn't really like, but it does this. The induced current flows in such a direction that its magnetic field in the center of the loop area where it counts is going to oppose the magnetic field that's into the screen, and so it's going to flow that way. Now be careful. Induced effects do not oppose magnetic fields always. They oppose changes in magnetic flux. In this case, the direction is opposite because the magnetic flux is increasing. If I had been pushing the bar the other way, the induced current would have gone the opposite way. The opposition is not to magnetic fields themselves, it's to change in magnetic flux. So we've got the direction counterclockwise in this case, and we're coming toward the end here. We've got the current, we've got the voltage. We've got the electrical power, P is IV. Multiply those two together, I got B dV squared over R. That's the rate at which electrical energy is dissipated in the resistor. That's one thing we needed to know. The magnetic force on the bar, we found that the magnetic force on a current-carrying wire is the current times the length of the wire, in this case D, times the magnetic field, so it's IdB, and as I pointed out, it's to the left. The force you need to apply for constant velocity would be a force in the opposite direction, like that, to make zero net force. So the velocity would be constant. So I need to apply a force of magnitude IdB to the right. But I know I. And I is B dV over R, so put B dV over R in there. You got two B's and two D's. They get squared, and that's to the right. That's the force. Force times distance is work. So force times distance per time is rate of doing work or power. So here we have those two results, electrical power, the force, and the rate at which I do work is the force times the distance per time, or force times velocity. There it is. Work that all out, and those two are exactly identical. The rate at which electrical power is dissipated in the resistance is exactly equal to the rate at which I do work. So magically, mysteriously, electromagnetic induction is taking the work I do from metabolizing my food and running my muscles and so on, and turning it into electrical heating of that resistor. Magically, the process of induction, well, not magically, but the process of induction knows about conservation of energy, and it does that. So we have a way of converting mechanical energy into electrical energy and into other forms using electromagnetic induction. A remarkable process, and one that really gives us a deep insight into a relationship between electromagnetism and the rest of physics. Okay, well, let's wrap up. Induction is not just about circuits. As I indicated or hinted earlier on, a full statement of Faraday's law says a changing magnetic field produces an electric field. Here's an example. If I had a magnetic field and it was pointing into the screen and it was increasing in strength, there would appear in its vicinity an electric field whose field lines form closed loops. There's no charge involved in forming this field. It's formed by the changing magnetic field. The field lines don't begin or end. They look more like magnetic field lines, but they are electric field lines. This is an induced electric field. And just to show you some glorious mathematics, the full statement of Faraday's law, and I put some arrows on there to show you the direction, and you can figure that out if you'd like, but the direction has to be consistent with Lenz's law. The full statement of Faraday's law has this beautiful form. It talks about how the E curls around itself. That's what's on the left. And on the right-hand side is something that involves time rate of change of magnetic field. So induction is about changing magnetic fields, making electric fields. Let's wrap it up. Electromagnetic induction is this new phenomenon in which a changing magnetic field produces an electric field. It gives rise to induced voltages and currents in circuits. The magnitude of the voltage is the rate of change of the magnetic flux. The induced current follows by Ohm's law. And the direction of the induced effect is such as to oppose the change that caused it. And that is consistent with conservation of energy. So we're done. But before we quit, if you like mathematics and like to think about these things, because induction is a great puzzle, let me give you a quick challenge. So here's the challenge. In that example I worked out in the onset monitor conserving energy, replace the resistor with a battery and leave the bar initially at rest and describe the bar's subsequent motion. And find a mathematical expression for its final speed. There's the challenge. Okay, let's look quickly at the solution. Here's the situation. We put a battery across there. We're going to get a current going clockwise. So the battery drives a current clockwise around the circuit. The current flowing in the magnetic field causes the bar to experience a force. And if you work out the force direction using the right-hand rule, you'll find it's to the right. So the bar starts moving to the right. Great. But as it starts moving, it not only moves, it accelerates. As it starts moving, the magnetic flux through the battery, bar, and rail system increases, just like as it did in our example, and that causes an induced voltage that opposes the battery current. And as the speed gets bigger and bigger, that voltage gets bigger and bigger, and eventually the bar experiences no force because the induced voltage is equal to the battery voltage, and it moves at constant speed. And that occurs when BdV, which was the voltage, the induced voltage we figured out, equals the battery voltage, and you can solve that for V to get the expression that's shown there. So if you've handled that problem, you really understand electromagnetic induction and a lot of electromagnetic theory.